This is Emily Clark at Quasi. Thank you for joining the Cyberseminar this afternoon. So Bridget and Rick, are you all set to get started, or do you want to wait another minute?
We're set. This is Bridget Scanlon, and I would just like to introduce you to the spring seminar series where we're going to focus on water and energy issues. And we have a sequence of 4 cyber seminars. And Rick Healy will be giving the first one on providing an overview of water energy nexus issues. And the second one will be by Barbara Beacons on induced seismicity. Mark Engel and I will talk about water and oil and gas. And Vince Tidwell and I will talk about electricity generation and sources of water. So Rick Healy is a hydrogeologist with the US Geological Survey in Denver. He's done a lot of work on hydrogeology, groundwater recharge, and other issues. His recent work has been focusing on water and energy, and he was the first author of a USGS Circular titled The Water Energy Nexus. So, Rick, go ahead.
Okay, thank you, Bridget, and thank you to everyone attending today. I hope you find the presentation of interest and the whole series of interest. I know it's a topic that both Bridget and I are very interested in. And thank you, Bridget, for setting up this whole series. So the outline of my presentation today, I'd like to give some brief introductory materials, then provide some background on water use and energy use within the U.S. Next, I'll talk about water use and water quality issues associated with fuel extraction and fuel processing, and then touch a little bit on water use and water quality issues associated with electricity generation. And then I would like to wrap up the presentation by discussing some of the science that we feel is needed for addressing the water energy nexus. We recently published this USGS Circular, the Water Energy Nexus and Earth Science Perspective. This came out last year, and if you're interested, you can get an electronic copy at this website. And if you're interested in a paper copy, I have a limited number of them, but if you want to email me, I should be able to get you a copy of one. Over the last few years, there's just been several reports coming out addressing various different aspects of the water energy nexus. And there are many aspects to it, engineering issues, policy issues, societal issues, business issues. So how our report differs from those is that we just concentrate on the earth science issues of both water use, availability, energy use, production, and how the two are interconnected. Okay, and so the presentation that I'm giving you today is more or less an overview of what's contained in this report. So the United States faces 2 important and sometimes competing challenges. Number 1, to develop sustainable supplies of water for humans and ecosystems. And number 2, to ensure the availability of energy resources. As our population increases, our energy use increases, our energy production increases. All of those signal a rise in the need for water. Okay. Every aspect of energy production and use involves water, both water quantity issues and water quality issues. Today, when resource managers are trying to make decisions on development of water and energy resources, they must weigh many factors, such as population trends, public opinion, societal behaviors, economics, human health, technology, and other factors. We as earth scientists, I feel, have a very important role to play in the decision-making process. And that role is to provide an earth science knowledge base upon which informed policy decisions can be made. So to build this earth science knowledge base, we first of all need to identify the important scientific questions that need to be addressed. We also need to conduct the research and the data collection to properly investigate those issues. And thirdly, and very importantly, we need to communicate our results to the decision makers and the general public at large. So the objectives of this presentation are to provide an overview of the important water energy issues and discuss the earth science research and data collection efforts that can enable us to more adequately address these challenges. There's two themes that constantly recur within the water energy nexus: uncertainty and trade-offs. Uncertainty shows up everywhere in terms of how much water we have available, how much energy resources we have, even in terms of our water use and our energy use. We have estimates for those numbers, but there's a large uncertainty associated with them. There's also a lot of uncertainty as far as the impacts of energy development on water quality, water availability, and ecosystems. Some of these impacts are readily apparent, such as increased demand for water and induced seismic activities. Those things can be felt pretty quickly. Other impacts may be more slowly to develop and more slowly to be identified, such as groundwater contamination. Another area of uncertainty regards climate change. We know that our use of energy is having a great effect on the climate. Okay, but there's a feedback associated with that also, that changing climate is going to change our water availability. It's going to change our energy needs and use. And so figuring out how climate is going to change and how that's going to affect our energy and water use, there's a lot of uncertainty there. In terms of trade-offs, one example is, options for reducing greenhouse gases may require more water and fuel. One prime example is carbon capture and geologic sequestration. We can do that, but when we do that, it's going to cost a lot of money. Also, it's going to reduce the thermal efficiency of our power plants, which means it's going to require more fuel and more water in order to generate the same amount of electricity. There's also trade-offs in terms of reducing air pollution, which may lead to water pollution. And a prime example of that was the addition of MTBE into gasoline in the 1980s as a replacement for lead to cut down on lead pollution. Well, it did that, but by the 1990s, we were finding MTBE in all of our water supply. So there's a lot of gray issues in the water energy sector. Water use within the United States. The U.S. Geological Survey since 1950 has published water use estimates on a 5-year interval, okay? And the biggest single use of water is for thermoelectric power. Thermoelectric power in 2010 accounted for about 45% of all water withdrawals within the United States. Most of that withdrawal goes to cooling at fossil fuel thermal electric plants. Okay, let me give you some definitions now. Water withdrawal is water removed from the ground or diverted from a surface water source for use. Water use is withdrawal for a specific use. Water consumption is that part of withdrawn water that is evaporated, transpired, consumed by humans or livestock, or otherwise removed from the immediate water environment. So all water that is withdrawn is not consumed. Going back to our previous slide, okay, in terms of water withdrawals for thermoelectric power, most of that water is returned to waterways, okay, it is not consumed. You know, we estimate that maybe 10% of the water that is withdrawn for thermoelectric power is actually consumed. So that's quite different from irrigation, where, say, 75% perhaps of the withdrawn water may actually be consumed. But water consumption, water withdrawal, they are both important, and we need to keep those terms in mind. Okay, energy consumption within the United States. This information is provided by the U.S. Energy Information Administration. On the left, this chart shows energy consumption, production, import, and exports for 1950 through 2013. And it's given in terms of thermal energy in trillions of kilowatt hours. Okay. Thermal energy relates to the energy content of a fuel. Okay. It's different from the kilowatt hours of electricity that we use. Okay. Give you an example, a coal-fired power plant may have a thermal efficiency, say, of 35%. Okay. That means that for every thermal kilowatt hour of energy consumed, 0.35 kilowatt hours of electricity is generated. In other words, almost 2/3 of the energy is not captured. Okay, a few things on this chart on the left. In terms of energy consumption, we can see the dip due to the recession in 2018. Also see a big dip around 1979, 1980 due to the oil embargo. Another important factor or feature here is the sharp rise in production of energy within the United States since the early 2000s. And that rise in energy production is mainly in terms of oil and natural gas, and it's been driven by new technologies such as horizontal drilling and hydraulic fracturing. Okay, on the right, we have a schematic here that's put out by the Energy Information Administration. This first column on the left shows the major fuel sources: oil, natural gas, coal, renewable, and nuclear. And the second column shows the end use category: transportation, industrial, residential and commercial, and electric power. So it shows you how much energy is being used and where that energy is being consumed. So oil is our largest energy source. It accounts for about 36% of our total consumption. Most of that oil goes to transportation fuel. Natural gas is about 27% of our consumption. That's pretty much split between industrial, residential, commercial, and electricity generation. Coal is at 19%, and our coal usage has been steadily shrinking over the last 10 or 15 years. Most of the coal consumption goes to electricity generation. Okay, renewables account for about 10%, and nuclear power accounts for about 8%. Okay, moving on to water and energy production and use. The chart just shows different aspects of energy development and use, from extraction or growing of fuels to processing, electricity generation, and end use in the different end use categories. Now, there's two issues of concern: water withdrawal and consumption, and water quality impact. And these issues occur in all of these items on this schematic here. And in the report, we go into some detail on each aspect of the fuel production, processing, electricity generation, and use. Okay, I mentioned that about 45% of withdrawn water goes to thermoelectric power, and that for withdrawal. In terms of consumption, we're looking at maybe 2 to 5% consumption of all water withdrawn for thermoelectric power plants, which may not sound like a lot when you look at the national scale, but when you break that down into regions, it can have a very different meaning. And I just want to point out, this is a map showing annual average precipitation in the U.S. And I just want to point out the western half of the U.S., which is mostly arid, semi-arid climate. This is an area where water is generally in short supply already. It's also an area that's predicted to have large growth in population, and then with the growing population, there will be an increased need for energy. It's also an area of much energy development, in particular North Dakota, Montana, Wyoming, Colorado. And that energy development needs water. Okay, so how is it going to get water in an area where the water is already scarce and the known resources are pretty much already allocated? Okay, water use and water quality for fuel extraction and processing. I'm going to talk briefly about the major fuels here: natural gas and oil, coal, uranium, and biomass. For natural gas and oil, we need water for drilling, for fracture stimulation, or fracking, and for processing. Now, Bridget and Mark are going to talk a lot more about water use for this in their presentation in 2 weeks. But just to give you an idea, a single well can require up to 50 million liters of water for fracking. What are the water quality concerns related to fuel extraction and processing? There are a number of concerns. Fracture stimulation, there's the possibility of injected fluids or lines that are resident in the reservoir already to be pushed into freshwater reservoirs. Transportation or infrastructure, and this would include pipelines. We all know that pipelines leak, and if we're transporting oil, say by rail or by truck, there's always a possibility of a spill and contamination. Produced water is basically the formation water that's present with the hydrocarbon. It can also consist of some of the water that's injected during the fracking process. But treatment and disposal of produced water is a huge concern in a lot of areas. Another water quality concern is, relates to the atmospheric emissions from drilling. And the prime one is methane, which is going to contribute to climate change, and climate change is going to impact both our water availability and water quality. Okay, moving on to coal. We need water to extract coal for dewatering, for washing, and for irrigation of reclaimed areas. There are a number of water quality concerns with the mining of coal. Perhaps the largest concern is acid mine drainage. Acid mine drainage occurs when rock with sulfur minerals is exposed to water and air. Oxidation reactions result in release of sulfur and the formation of sulfuric acid. And I think we're probably all familiar with the damage that acid mine drainage can cause. In the state of West Virginia alone, I believe there were more than 4,000 kilometers of streams that have been damaged by acid mine drainage. Another water quality concern is with stored water. And this is kind of rare, but can be extreme. To give you an example, back in 1972, a dam that was built with mine waste failed in West Virginia. And the resulting flash flood destroyed 500 homes and ended up killing 125 people. So this is a very serious event. Another water quality concern is related to ecosystem alteration. And the most obvious example of this is mountaintop removal mining. This photo here is actually of a mountaintop mine that is in the process of reclamation. But with mountaintop removal, basically the material overlying the coal bed is just removed and generally pushed into adjoining valleys so that the coal can be more easily extracted. Well, this can have devastating effects on the ecosystem of the watershed. Okay, moving on to biofuels. Again, we have water use and water quality concerns. Irrigation of corn that's used for production of ethanol is it's a substantial amount. When you calculate it on the look at the total amount of irrigation that occurs for corn and the amount of ethanol that is produced, you come up with an estimate of about 50 liters of irrigation used to produce 1 liter of ethanol. So even though biofuels represent only about 5% of our transportation fuels, they still account for about 50% of all water consumption related to transportation. Water quality concerns, the biggest ones are the use of fertilizers and pesticides. Streams and shallow aquifers in the Midwest part of the country are, a large number of them are contaminated with nitrates and some pesticides. Okay, moving on to water use and water quality concerns and the generation of electricity. Most of our electricity is generated at thermal electric power plants. And Bridget and Vince are going to talk more about this 3 weeks from today, so I will just touch on it shortly. Most of our thermoelectric power plants are coal or natural gas based or nuclear based. We also have geothermal and concentrating solar plants, but they really just account for a small fraction. Hydroelectric plants and wind and passive solar plants. Hydroelectric plants can actually use quite a bit of water when we look at them. This is just a photo of the Ivampa concentrating solar plant in the Mojave Desert in California. And this plant consists of 3 towers, each tower surrounded by about 100,000 mirrors that focus sunlight onto the tower to heat a fluid that is then used to boil water to drive a steam turbine. To give you an idea of the water intensity of thermoelectric power plants. Now, water intensity is defined as the amount of water that is required to produce a single kilowatt hour of electricity. So for coal, we're looking at 1 to 2 liters per kilowatt hours. About the same for gas. Nuclear is a little more. Geothermal and concentrating solar, even though those means of generating electricity are nice because they don't emit greenhouse gases, they consume substantially more water than the more conventional thermoelectric power. Water intensity of a hydroelectricity. The water use for hydroelectricity consists of evaporation that occurs from a reservoir above a hydroelectric dam. And we can just do some quick calculations for, say, Lake Mead, with a surface area of 364 square kilometers, average evaporation rate of about 2 meters per year. Okay, and so we can calculate a volumetric evaporation rate for the year, and we know how much electricity is generated by Hoover Dam. And with those numbers, we can calculate a water intensity. And that calculated value comes out to 180 liters per hour. Just to back up and compare that with other thermoelectric power plants, you can see that the hydroelectricity can be up to 2 orders of magnitude more water intensive than traditional thermoelectric power plants. But this analysis is a little, it's not exactly straightforward, because all the water that's in Lake Mead is not there just to generate electricity. Water in reservoirs can be there for a number of reasons, just water storage, irrigation, flood control, things like that. And we don't have any standard method for appropriating evaporation on the base of water reservoir use. And until we come up with that method, we really cannot come up with a water intensity for hydroelectricity that we can compare with other numbers. Okay, moving on to water quality concerns with generation of electricity. The concerns fall into 3 categories: atmospheric emissions, coal combustion products, and contamination of withdrawn water. Okay, and again, this is for coal. Atmospheric emissions, coal power plants are the single largest source of human emissions of mercury to the atmosphere today. Okay. We also know that coal power plants are a large source of greenhouse gases, primarily carbon dioxide. Okay. We also they can also be a source of significant sulfur and nitrogen oxide emissions. Okay, and these can lead to acid rainfall. Okay, and the greenhouse gases, of course, related to climate change. Okay, just to give you an idea of how things have changed in terms of acid rain, in the last 30 years. These two maps from 1985 and 2012 show you there's been a dramatic improvement in acid rain over this time span, primarily related to new laws on catalytic converters for vehicles and for emissions controls on power plants. Okay, another important source of possible water contamination is coal combustion products, or coal ash. This is the amount of coal that's left after combustion. And on a per mass basis, about 13% of the coal that is burned comes out as coal combustion products. Some of this water can be, or some of these products can be reused. We can obtain gypsum out of them. Some of the material is used for building products like bricks and in roads also. The amount, about 50% of the coal combustion products are reused. The other 50% are stored or disposed of in waste disposal sites. Another important source of contamination for withdrawn water is heat. If we raise the temperature on streams, that can have a very deleterious effect on the ecosystem of the stream. So there are regulations on how much a power plant can raise the temperature of a stream. And of course, this is most critical during times of drought, which are usually the hottest times of the year. And so those restrictions have led to reductions and sometimes the actual shutdown of power plants because they cannot get the cooling water that they need. Okay, water quality concerns in terms of natural gas for generation of electricity. The water quality concerns are not as great for natural gas as they are for coal. We do have some greenhouse gases, but the amount of carbon dioxide emitted by gas-powered thermoelectric power plants is about half that emitted by coal plants. Okay, we can still have some nitrogen oxides emitted, and we still have the concern about raising the temperature of the withdrawn water. In terms of nuclear power plants, there is the danger of a meltdown. This is a very rare occurrence, but the consequences are absolutely devastating, as we have seen. And again, the common problem of raising the temperature on the withdrawn water. Okay, so moving on now to science for addressing the water energy nexus. There's we've outlined the different scientific issues in terms of research and resource monitoring and assessment. And this distinction is really not a good one, I don't think, in my mind, because we cannot do research without doing monitoring and assessment. And on the flip side, we need the research in order to try and explain the trends that we see with our monitoring and stuff. So these are the different topics that we've identified and that we go into some detail on in our report. And I'm going to talk in a little more detail on some of these. Freshwater availability. And that includes both water quantity and water quality, because whether we have water available for a particular use depends, on the quality of the water that we need for that use, the quality of the water that we have, as well as the quality. Water use is another area where we need to do more work. As I said, we have 5-year estimates of water use, but there's a lot of uncertainty in all those estimates, and we need to do more to reduce that uncertainty. Ecosystem health, I will talk about a little bit more. Saline groundwater, I'll talk a little bit more. Fossil fuels, uranium, geothermal resources. I'm not going to say too much more about that, but just simply because we don't have time this afternoon. But there are a lot of areas for research in terms of development of geothermal resources. It's estimated that there's enough geothermal resources out there to provide up to 50% of our electricity needs. And in order to tap into those resources, we need to further develop what's called enhanced geothermal systems, whereby we can introduce water to hot rock systems, pull the heat off of those rocks, and recirculate the water. Okay? And again, we talk about that more in this report. Induced seismicity, Barbara Beacons is going to talk about that next week. I very much look forward to that. I've mentioned climate change, byproducts and waste streams of energy development. We talked about, the coal combustion products and how those might be used, and either used or treat the waste products and find some safe way of disposing of them. And another item that we discuss is emerging energy technology. It's tough for us as researchers to stay on top of all the emerging technology because the energy companies are out ahead of us. They developed the means for fracking long before we understood much of the implications on water quality. But we need to stay involved as much as we can on these emerging technologies. Okay, in the last few minutes, I would just like to touch a little bit, in a little more detail on a few of these research topics. And first is availability of fresh water. Research and assessment needs. A water census. It's been more than 40 years since the last national water census. And that last water census was not very detailed, and things have just changed dramatically in the last 4 decades. There is a current effort on a water census that's being overseen by the Federal Advisory Committee on Water Information. The USGS is heavily involved in that, as are several other federal agencies. Another thing we need to do is just reduce uncertainty in our understanding of the watershed water budget. It sounds very fundamental, and it is, but we can gauge streams, we can measure precipitation, but anything we can do to reduce the uncertainty in all these measurements will help. Now, another nice thing to have would be a national groundwater monitoring. some of you may find it surprising that here in the United States, we do not have a national groundwater monitoring. We have a surface water monitoring network, but no groundwater monitoring network. Now, many states and regions have their own monitoring networks, but they're not tied together on a national basis. And this has been one of the suggestions of this Federal Advisory Committee, is to establish this groundwater monitoring network. Okay. In terms of availability of fresh water for energy needs, it would be great to expand monitoring in areas of energy development, and also to integrate models of water quality and ecosystem health. And I'm going to add in here, it would also be good to integrate our monitoring networks for collecting data. Because we have groups out there that are collecting hydrologic data, we have groups collecting energy data, we have groups collecting ecosystem data. If we could somehow integrate all those data collection efforts, I think it would benefit all parties. Okay, another area that we highlighted for research needs is for saline groundwater resources. And we already use a fair amount of brackish and saline groundwater resources in the U.S., okay? This is for use in 2010. It just shows the total high TDS groundwater use in cubic meters per day. High TDS is groundwater that has a total dissolved solids concentration greater than 1,000 milligrams per liter, okay? Primarily, this usage is occurring in the western part of the country. And what the water is being used for, in some cases it's being used for public water supply. It's also being used for irrigation, for livestock, for hydraulic fracturing and other energy uses. There are some power plants that use saline groundwater for their cooling system, aquaculture, mining, or other uses. In terms of the information that we need to know more about the availability of these brackish and saline groundwater resources. What is the water chemistry of these groundwater systems? What are the physical hydraulic properties of these systems? And how are these systems connected to freshwater systems? And will use of these saline resources somehow impact our freshwater resources? Okay, another item that falls under climate change, where there is a lot of research going on right now, is for carbon capture and geologic sequestration. And the idea is to collect the carbon that is now being emitted from big sources such as power plants, and then to pressurize that carbon dioxide into a liquid and then re-inject it into the subsurface. There's several concerns here. As I mentioned earlier, this is going to be a very expensive process. And there's the possibility of contamination of freshwater resources from carbon dioxide or displaced saline water. There's also a potential for induced seismic activity. And I mentioned earlier that collecting the CO2 emissions is going to result in a reduction of thermal efficiency of our power plant, which leads to increased fuel and water consumption. Research needs identify potential storage formations, determine the physical properties of the formations, determine the geochemical properties of the formations and the groundwater, and develop an understanding of the potential physical and chemical interactions among injected fluids, groundwater, and the formation. Okay, I'm going to skip over ecosystems and just go to the summary here because we're running short on time. So just to summarize, water and energy development are linked in many important ways. And earth scientists have an important role to play in decisions on resource development. And that role is to provide an earth science knowledge base upon which informed policy decisions can be made. And this includes identifying the underlying scientific questions, conducting appropriate research and data collection, and communicating the results to the general public and research. So I thank you all, and Bridget and I would both be happy to entertain any questions that you might have.
Yeah, so if anyone has any questions, please type them into the chat box and we'll read them out loud and Rick will answer them.
Thanks, Steve, for your positive comments and your support. We appreciate it.
All right, we have a few questions coming in.
Okay, yeah, the Steve K asked about the ecosystems. And let me just quickly go through that. Concerns with energy development from an ecosystem perspective. Well, there's enhanced competition for fresh water, especially in times of drought. There's water quality issues, air quality issues. Land use change is a huge one for ecosystems, and climate change is going to be in terms of priorities for monitoring and research, we need to enhance our monitoring, standardize our monitoring methods, and as I mentioned, integrate monitoring, ecosystem monitoring along with our water and energy network. Another big concern is that there's no standardized means for assessing and valuing ecosystem services. Now, how do you put a dollar amount on ecosystem services? It's very difficult, and that makes it hard for resource managers to weigh those factors evenly. And we also mentioned that it would be good to develop enhanced decision support systems based on integrated models for climate, water, land use, and okay, Matt Findlay asks, is there any data out there on how water for fracking compares with water used for processing gas and refining petroleum? Yes. The Bridget and Mark are going to give a more up-to-date presentation on water use for fracking. In terms of water use for processing gas and oil, we have some of those numbers in this report. And in general, it's going to be small compared to what's used for fracking.
Rick, maybe I'll add to that the water used for hydraulic fracturing in, say, some of the plays in Texas and in the Marcellus relative to that used in power plants, it's about 6%. So water used to extract the gas using hydraulic fracturing is about 6% of the water consumed in the power plants to generate electricity with that gas.
Okay, Luke asked, does land application of wastewater emerge as an important environmental concern for some of the energy production methods? I don't think that land application has been done in large scale for energy production. It has been done some up in the Powder River Basin, Montana and Wyoming, where they're using some of that water for irrigation purposes. But that water is relatively low in total dissolved solids, probably between 1,000 and 3,000 milligrams per liter. Most produced water is substantially higher than that in EDF. Are most slides presented in the circular? Yes, most of these slides were taken from the circular. Yes, I believe that this presentation will be posted on the Quasi website for anyone to download.
So oh, go ahead.
Sorry.
We'll go ahead and post the recorded presentation to the Quasi website, and Rick, if it's okay with you, we can post the slides for downloading as well.
That is fine with me.
Okay. So if there are no other questions, it seems like we can end the presentation for the day. So Rick, thank you so much for your excellent presentation. And again, we will post the recording to the Quasi website. Just a reminder, we have the following presentations remaining in the series. So on March 18th, which is next Friday, Barbara Beckins from USGS is going to talk about induced seismicity. Followed by Mark Engel on March 25th, and Bridget Scanlon and Vince Tidwell on April 1st. And again, that will be at 3 o'clock p.m. Eastern Time. And while you're all here, before you sign off, we have a few upcoming Quasi deadlines to draw your attention to. Just some workshop deadlines that are closing, as well as the National Water Center Innovators Program applications are due on Tuesday, March 15th. So if you're interested in any of these workshops or programs, please check them out and apply or register soon. So again, thank you so much, Rick and Bridget, and we will hopefully see you all for next week's presentation.
Thank you.
Thanks.